Most of the substances we run into every day are not elements, they're compounds. It's actually unusual to find free elements in nature. Compounds, as we've talked about before, a compound is different from a mixture of elements, because in a compound, those elements are combined in fixed, definite proportions. If you decompose water, you find that the ratio of the mass of oxygen to hydrogen is always 8 grams to 1 gram. It's a definite proportion. In a mixture, the components can have any proportions. You could have a little bit of one or a lot of one. It can vary. So here we have a balloon with a mixture of hydrogen and oxygen. So hydrogen molecules, oxygen molecules, the ratio is variable because they are individual particles. We can tell this is a mixture because there are 2 different kinds of particles in there. And you could have more red ones or more white ones. You could vary the proportions. The first time I saw this picture, I'm like, what the heck am I looking at? This is a balloon that was filled with water and has popped. And they caught it as the balloon skin was retracting from around the water before the water just fell on the floor. When I first looked at that, I'm like, what the heck? Anyway, so this is a water balloon. Water is also hydrogen and oxygen. But it's not a mixture, it's a compound. So the water here has very different properties than the hydrogen and oxygen in here. If you put a match to this balloon, it's going to go kaboom, because oxygen and hydrogen mixed together are very, very flammable. If you put a match to this balloon, the rubber would pop, the latex would pop, and then the water would put out the flame. Those are pretty different. Explosive or putting out fires. In water, which is a compound, all of the particles are the same. And we always have this fixed ratio of 1 oxygen atom to every 2 hydrogen atoms. They're all the same. You can't have water that's got a little more oxygen or a little less hydrogen in it. Water is water. So Joseph Proust lived back in the late 1700s, early 1800s. He was the first one to formally state this idea that elements combine in fixed proportions to form compounds. So this is known as the law of constant composition. All samples of a given compound have the same proportions of their constituent elements. It doesn't matter where the water came from. You pull water molecules out of the Kings River, you pull water molecules out of the ocean, pull water molecules out of the Nile River. The water is the same, no matter where it came from. It's always the same proportions of the elements. So, if we take 18 grams of water and we decompose it, we're going to get 16 grams of oxygen, 2 grams of hydrogen. So we could take the mass of the oxygen, divide by the mass of the hydrogen, and we get 8.0, or a ratio of 8.0 to 1. It's 8.0 because this number has 2 sig figs. Why did we put the oxygen on top and not the hydrogen? Because this was a bigger number, and it's nicer if you get whole numbers instead of decimal numbers. So this is true of water, pure water, no matter where it comes from. The reason that compounds have these constant composition is because they're composed of individual building blocks, and those building blocks are always put together in the same way. If you always have 2 white balls and 1 red ball, the ratio of the masses is always going to be the same because the numbers of the things are the same. 2 samples of carbon monoxide obtained from different sources are decomposed into their constituent elements. One sample produces 4.3 grams of oxygen and 3.2 grams of carbon. The other sample produces 7.5 grams of oxygen and 5.6 grams of carbon. Are you bored yet? Are these results consistent with the law of constant composition? Wow. There were a couple of questions like this on the first homework assignment that people kind of are, what the heck do we do with this? It's an important idea. It's not an important skill to be able to solve a problem like this. Well, what do? Well, pull numbers out, right? That's kind of the approach. Read the question, pull out the numbers. So we have 2 samples here. One sample and the other sample. Let's call them 1 and 2. So this is number 1, and over here we'll say this is number 2. So one sample, 4.3 grams of oxygen, okay? 4.3 grams, and I'm just going to write O because that's a symbol and I don't have to write the word. 3.2 grams of carbon. 3.2 grams of carbon. The other sample gave us 7.5 grams of oxygen and 5.6 grams of carbon. Why didn't they give me the same mass of oxygen? They're different samples, they're different sizes. Which sample was larger, number 1 or number 2? Number 2. It's got more mass in it. So to find out if these are consistent with the law of constant composition, we're going to look at the ratio of elements. So they're both oxygen and carbon. I'm going to choose the bigger number and divide it by the smaller number. So I'm going to do 4.3 grams divided by 3.2 grams. Oops, 4.3 divided by 3.2. And I get 1.34375. Are all of those digits important? Do we need to write them all? No. So these masses are somewhat approximate. They're to the nearest 0.1 gram. 2 sig figs, so we can round this to 2 significant figures. So the ratio there is 1.3, or 1.3 to 0, to 1. So the mass of oxygen to carbon is 1.3 to 1. Well, let's see what the ratio is here for sample 2. 7.5 grams divided by 5.6 grams. So that gives me 1.339285,714. This number is not exactly the same as that number. I thought the ratio was always supposed to be the same. Well, these are not exact numbers. So when we round the number based on the precision, the number of sig figs and what we started with, we're going to get 1.3 again. 2 significant figures and 2 significant figures. So this also gives us a ratio of 1.3 or 1.3 to 1. Any questions? Does that support the law of constant composition? Yeah. Well, ratios are often one thing to another, right? And so if I just divide these numbers, I get a number. That's the same as 1.3 over 1.
Okay. And is the variation between the two different values that you got due to isotopes?
No, it's probably not. The variation is probably not due to isotopes because we're dealing with such a huge number of atoms. The slight variation here is due to the uncertainty in the measurements that were made. Any questions?